Hello everybody. So today I'm going to show you how I solve this question. So the question is to find a numerical solution for the heat diffusion. So yeah, this is UT is equal to 1 UXX, and yeah, so we have X is from -5 to 5 and T from 0 to 100. And these are the boundary conditions. So both aims are strict to be 0, and this is the initial the initial temperature. So using the backward time center space, it's given that I have to use delta t equal to 0.05 and delta x for 0.1. And in the last one, I'm going to plot the solution in the xt plane. So firstly, I define the parameters in Python. So have the length from -5 to 5. It's called a spatial domain. So the spatial step, I call it dx, which is 0.1, and for the time step it's 0.05. And according to this, the diffusion coefficient or alpha is 1, and the final times t it's 100. Okay, now I print out to check if it's correct or not. And then for the next one, it's a grid setup. So I define the length of the 1D heat diffusion is from x right minus x left, which is just 10. And for nx, it's the total length divided by dx, and it includes both endpoints, so you have to add 1. And for nt, it's t final, which is 100 over dt, which is given, and we have the number of time steps for spatial grid. It's from x left to x right, which is -5 to 5, with this grid, and the time grid, including t0, it's nt plus 1, from 0 to t final, which is 100. So in total, we have nx equal 101 and nt equal to 2000. And for the next step, we calculate lambda from this equation. So we have alpha, which is equal to 1, and dt, which we had above, dx above, the x squared here. So we have lambda equal to 5. Okay. To the next step, we build coefficient of matrix A and apply the boundary conditions. So we have this equation. We just need to substitute and get matrix A. So firstly, we're gonna initialize the coefficient matrix A as showing here, and this is a new variable named equal to 1 plus 2 times lambda of, yeah. And to the next one, we fill the interior rows with these codes. And next one, we have to apply the boundary condition using the Dirichlet, which it says that at -5 and 5, you have temperature equal to 0 at the end. And we're gonna print the matrix here. It's a matrix 101 times 101, so it's a very big matrix, but yeah, we can print just 10 times 10 just to see the pattern here. And to the next step, we do time stepping to solve the BTCS linear system. So first, we initiate the initial condition at t equals 0. So E0 is 0 and like that. And this one, I'm just ensuring that the boundary rows in a identity u plus minus 5t equal to 0, and this is held for all t, and it's written here. And allocate storage and perform BTCS time stepping. These. And now BTCS is solved. So in the next step, we're gonna visualize the solution. This one, I just first I made a heat map here. This is the code for the heat map, but I think it's a little bit difficult to see because like it's quite a big space. So I plot graphs, but it's like a 100 graphs. So I only choose some of the times to plot. So we have something like this. So this is the initial state, and when time passes, the temperature diffuse over time and flattens out. I also did make a 3D illustration. So this is time t, and this is the spatial coordinate x, and in the z-axis is the temperature. So this is time. So when time passes, the energy, the heat diffuse. Yes. Okay. Thank you for listening.